right, so we are starting a new chapter here. Chapter 10 is on sequences and summation notation. So it's kind of a generic overall look at sequences before we dig into a little deeper for the next few days. As we come across sequences, there's going to be certain ones that are kind of common to us or ways that they are created. Here's just a few to look at. I have this first one, 1, 4, 9, 16, 25. You kind of have to have like an awareness of numbers and recognize that when you look at that, oh, those are all perfect squares. So we're going to come up across these perfect squares. You need to know that, oh yeah, those are perfect squares. Okie doke. Let's look at the next one. What do you think on that one? All right, so some people look at it, well, most people look at it and say, oh, I'm just doubling it. Every time I'm doubling it, doubling it, doubling it. Okay, which is very true. That is exactly what's going on. That is a recursive way of looking at a sequence, of saying, what am I doing to get to the next one, to the next one, to the next one? This is, like I said, it's a recursive mentality, and that's great. However, if I wanted to know what the 50th term in that sequence is, that would be a little bit tedious to get to, because if I'm just going to keep doubling, the only way I'm going to get the 50th term out here is if I know the 49th term. And to know the 49th, I got to know the 48th. And so the only way to get to the 50th is to know all 50 terms. So let's look at it in a more explicit way, where just boom, what do you know each one of these numbers is? All right, so that's a little deeper, maybe thinking, but hopefully you could look at that and say, well, I think those are all powers of 2. This is a 2 to the 0. This is a 2 to the first, 2 to the second, 2 to the third. So you can look at the first term is to the 0, the second term is to the first, third term is to the second. So if I did want to know that 50th term, well, it would be 2 to the 49th. And so, boom, I would just know it. I don't have to know the whole list to get to that 50th term. That's an explicit way of looking at it. Okay, the next one's a totally different, well, I say totally different. It's not really totally different, but it's a famous sequence. And since I guess you're watching the video, I'm just going to give it away. But the way to get to a particular number is to add the 2 numbers before it. So this is a 2. I added the 2 numbers before it. To get the next term, I added the 2 numbers before it. To get to this term, added the 2 numbers. All right, so let's keep it going and keep it going. And could you tell me like the next 3 terms for this? So 13 was the sum of 5 and 8. So now I'm going to take the sum of 8 and 13, and I would get 21. The sum of 13 and 21 would be 44. I'm sorry, 34. And then 21 and 34 would be 55. And we could keep going and keep going. Okay, that is called Fibonacci sequence. It's the one that's in all the movies. When they need a sequence, it's like the password, the secret password. That's what it is, Fibonacci sequence. Now, Fibonacci sequence is partially famous because it has a lot of occurrences in nature. When you look at plants and different things in nature, I'm going to talk about a few tomorrow about where this Fibonacci sequence actually occurs in real life. Let's talk through some notation. When we talk about a sequence, we use this notation right here. It's an A with a sub number of n. And we don't really call it A sub n, and we don't say A to the nth, because a lot of people want to say A to the nth. Nope. We just say that's the nth term. With that A with the sub number there, it just means it's some number, and this indicates which term number it is. So if I was doing the Fibonacci sequence, this would be the first term is 1, the second term is 1, third term is 2. So that's how you say this. The sixth term is 8, not A to the 6th or A sub 6 or whatever. It's just 6th term. Now we're going to look at 2 types of rules here today. One of them is the recursive rule that I referenced, and then the other one will be the explicit rule. So let's start with the recursive rule. It defines the nth term of a sequence as a function of the one or more terms that precede it. So you're always going to be given like the first term, whatever it is, and maybe the first few terms. And then they're going to give you like a function that is defining what the pattern is that you're supposed to follow. So you have to kind of understand where terms are in reference to one another. So if you think of like I'm looking for the nth term, the one right behind it would be called the n minus 1 term. And if it was 2 behind it, it'd be the n minus 2 term. If I'm looking ahead, this is the n plus 1 term, n plus 2 term. But really, you just have to know like where these would be. I kind of made this list for you to look at. But if I was looking for the n plus 3 term and I was referencing the n plus 1 term, you would need to recognize, oh, well, that would be the term that would fall 2 before it. Or if I was looking for the n plus 4 term and I referenced the n minus 5 term, well, okay, that'd be way down here. All right, so just knowing where they are in reference to one another. Let's do a few. So this one says find the first 5 terms of the sequence defined by, all right, here they are. They're giving me the first term is a 4. I have to find 5 terms. Here's the first one. And then here's the rule that they're giving me. To find the nth term, I'm going to take 2 times the n minus 1 term and then add 1. Okay, so if you think about this, to find the nth term, I'm going to take and so really it's to find a term, I'm going to say, to find a term, I'm going to take 2 times the term, look at this, it'd be the one right before it, so 2 times the term right before it, and then add 1. And that's just the rule that I sit there and do over and over and over. So looking at this one, if I were to list this out, and I'm going to go ahead and just list it like with commas here, it's going to be a 4. And now, what to find the next term, I use this little function. So 2 times, so I'm looking for this term right here. So it's 2 times the term before it, so that'd be an 8 plus 1. So that term would be a 9. To find this term, the function's telling me take 2 times the term before it and add 1. Well, that'd be an 18. Add 1 is a 19. All right, let's keep going. Take the term before it, double it, that'd be 38. Add 1. Take the term before it and double it. All right, that'd be 78. Add 1, that's 79. All right, so there's my first 5 terms. Now we're going to practice this. This is probably the most common scenario and probably the easiest to understand, so I'm going to challenge you a little bit beyond this. But if I'm looking for a particular term, this would be the term right before it. But we can make it more challenging than that. Now you have a homework worksheet here. Hopefully, maybe you have that in your hands right now. If not, we're just going to review these 3 from it, and then when you get a hold of the worksheet, you'll finish it out. But I just picked some random problems off of that. And so here we go. On each one of these, they're going to give you a starting term or maybe a couple starting terms, and you're going to fill those in. And then it's going to give you this function that you have to use to figure out what the pattern is to fill in these 3 bold lines. And then it's kind of like a little riddle worksheet, so you can kind of check and make sure that when you come up with these last 3, that it matches. You can find a match in the key of the box of your worksheet. Now, on this one, the first term is a 10, so I put a 10 here. And then the rule is saying, okay, so to find a term, I'm just going to call it a term because I know this is the term right before it. So to find a term, I'm going to take the term before it and subtract 3. So to find this term, I'm going to take the term before it and subtract 3. Term before it, subtract 3. Term before it, subtract 3. All right, and then you can look for 741 over in the box and see what if that matches to. All right, let's jump to number 8. They're giving me the first term is a 4 and the second term is a 3. Now let's look at what the rule is. The rule says to find a particular term, you're going to take the term right before it and you're going to add. Now think about where this one is. Isn't this the one that's right before this one? So ultimately, this is like the Fibonacci sequence. To find a term, I'm going to add the 2 terms that are before it. Now, the reason it's not really Fibonacci sequence is because it didn't start with 1 and 1. Fibonacci sequence always will start with 1 and 1. But the idea is the same. Add the two terms before it. Add the two terms before it. Add the two terms before it. All right, so now we're getting fancier. We're to number 4. I'm giving you the first term, the second term, the third term, and the fourth term. So apparently we're going to be using a lot of terms here to figure out the pattern. So now I'm going to go over here. Now notice it's not really looking for the nth term, but I'm just looking for, even if it's the n plus 10 term, that's fine. You have to know, where do these two terms fall in reference to where this one would be. So when I look at this, the n plus 10, wouldn't the n plus 8 just be 2 before that? And the n plus 6 would be 2 before that? All right, well, that's the pattern. So to find a particular term, I'm going to take the number 2 before it and multiply it by the one that's 2 before that. So when I'm down here, I'm going to look at the number that's 2 before it, so that's the 5, and multiply it by the one that's 2 before that. That's a 1. So 5 times 1 is 5. All right, so now I'm going to find this one. Take the term that's 2 before it, that's a 2, and multiply it by the one 2 before that, that's a negative 3. So this would be a negative 6. All right, I'll give you a second. Why don't you figure out what that next term is going to be? All right, hopefully you got a 25. It'd be the 5 times the 5. Okay, so if you have that riddle worksheet, it is part of your homework. Why don't you pause the video and go practice that a little bit before we keep moving? All right, so now I'm going to move on to explicit rules. I feel like they're a little bit handier because they're not as dependent on knowing the entire sequence to get to a certain term. Now, explicit rules kind of depends on the textbook. Sometimes they call it the general term or the nth term. A lot of ways to say it, but it's pretty much just a straightforward rule. It's used to find a particular term. So we're going to kind of do the same thing we just did, only I'm not going to get tied up into using so much of the pattern of numbers. I'm just going to keep plugging things in. So I'm going to look for the first term. So the first term looks like this. But what I'm indicating here is that I'm going to put a 1 in for the n. So here's the function. When I put a 1 in for the n, that'd be 1 squared times 3. That's 3 minus 4. That'd be a negative 1. So the first term, I guess maybe I should show that for the sake of your notes at least once here. What I'm doing is I'm putting a 1 in there. Okay, so then we end up with that equaling negative 1. So the first term is negative 1. The second term, I would be putting a 2 in for the n. So it would look like this. So then order of operations, I'd have 2 squared, that's a 4, times the 3, that's 12, minus the 4, that's an 8. Now, I feel like these rules usually are not super complex, so I'm really not going to be showing all of this work other than for you to have it in your notes so you knew where your answer came from. I'm just going to do it in my head right here. 3 squared, that's 9, 27 minus 4. All right, that's going to be a 23. Fourth term, they want 4 terms. All right, 16 times the 3, that's a 48, minus 4, we get 44. Now, I like to kind of show this in this format so you see that this is the number that's getting pulled in. But this is also a lot of writing. You spend way more time writing it than you ever do actually calculating it. So on this next one, or maybe I'm going to do this one more time, but then we're going to start looking for what's a shorter way to maybe write that. So here we go. I'm going to do one more with you. So the first term means I got to put a 1 in. This is a little bit more complex of a problem because you've got this power going, you've got a fraction. This is definitely amps up the difficulty level. So I've got a 9, and this is going to be a negative 1/3 to the first power. Okay, so that's not terrible. 9 times 1/3 would be 3, but it's going to be in a negative 3. If I want the second term, now I'm going to be taking this negative 1/3 and squaring it. Can you do that in your head? Okay, hopefully you're getting a positive 1/9 times 9 would get you a 1. All right, if it's cubed, getting trickier here. If I take it to the third power, now this time I'm going to shortcut and just write the answer. If I take that to the third power, it's going to be a negative 127. If I take that times 9, I'm going to end up with a negative 1/3. And the fourth term, what do you think? Right? Hopefully you get a negative 1/9. Now, this is an explicit rule, but I do want you to kind of notice here, if I had just listed these out, do you feel like you could have come up with a recursive pattern here? Do you see what's happening every time to get from here to here to here to here? All right, hopefully you're seeing that you're dividing by a negative 3. Or maybe an easier way, as this list gets longer and longer, you're multiplying by a negative 1/3. And actually, by me just saying that, I just caught this. Wouldn't that be positive? Yes, that would be positive. Did you catch that? Positive 1/9. Okay, let's try one more. Now this one I'm going to have you try on your own. It's got its own special features here that makes it a little bit trickier, but I still want you to give it a shot. We're still finding the first 4 terms. See what you can do with this. Go ahead and pause the video for a moment. All right, so here's what I got. When I put in and I looked for the first term, that means I'm putting a 1 in for the n. If I put a 1 in for the n, that's going to turn that into a negative 1. And then 1 squared is just 1. So I end up at negative 1. Okay, second term. What I'm going to do when I square the negative 1, that's going to turn to a positive 1. And then I'm going to have a 2. Oops, I didn't write the squared up there, but it would have been squared. Okay, so that's going to get me a 4. Third term. If I take it to an odd power, I'm back to a negative 1. And then I'm going to take my 3 and square it. So now I'm at a negative 9. And you probably can pretty quickly figure out the pattern. And it's not terrible if once you figure out the pattern, are you just doing this recursive thing or figuring it out, just noticing what the pattern is? I know the even power is going to make it be a positive 1. And then this is just going to always be the perfect squares. So I can see by looking at what's going on here, the negative sign is going to alternate positive, negative, positive. Other than that, these are just perfect squares. But that positive or negative, positive, negative, positive, that right here happens with this. And we're going to want to keep track of that little trick because we do use that a lot on sequences that alternate sign. Now, the one thing I do want to, I guess for this, these are your notes, right? Let's make a note. What did we find out? The signs will alternate. And that's how we make it happen, by doing that little trick right there. Now, one thing I would make note of here, though, is what if the signs alternated, but the first term was positive, then negative, positive, negative? Okay, so we would have to do something here that would make the first term end up positive. And if I want the first term to be positive, I can't be putting a 1 in right here. So what I typically do, what is standard for that, is they would change it. Another alternative would be to do a negative 1 to the n plus 1. So that way, my first term, when I put a 1 in for n, it actually ends up getting squared, which is then going to make it positive. So this is how we would do it to make it go positive, negative instead. So these are 2 separate options of what you might do. All right, so we have one more type of pattern that we're going to see. And this kind of is just getting you familiar with this because I'm not sure that you're going to necessarily remember it that well. You would have seen it in college algebra, but it's something we call factorial notation. And we do use it a lot in probability, and that is coming down later on in this chapter. So here's what factorial does. When you have a number factorial, that means take a number times every number below it. All right, and then one little, well, let's go ahead and try one. Let's do 5 factorial. That just means take 5 times 4 times 3 times 2 and times 1. And you end up at 120 when you do that. Now, some of these you're going to get familiar with because we use them a lot. I don't know, probably nothing bigger than 5 factorial you're going to have memorized, but like I said, probably up to 4 factorial you'll know pretty quickly. So this pattern of this 5 factorial, that's going to pop up in different rules that we create. It's going to pop up when we do probability. One just quick thing up here is that 0 factorial is defined to be 1. It feels like it should be 0, but it's not. It is defined to be a 1. Okay, so let's use this factorial idea to figure out what are the first 4 terms of this explicitly defined sequence. So to find the first term, I'm going to put a 1 in for n here. That's going to be a 2 to the first. And I'm going to put a 1 in down here. That's going to be 1 minus 1, which is 0 factorial, which we just said is always equal to 1. So I'm going to end up with a 2 over 1. So my first term is a 2. All right, now we're going to find the second term. So that means putting in a 2 here. So that would be a 4. Put in a 2 here, that'd be a 1 factorial. That's just 1. 4 over 1 is 4. All right, let's try the third term. 2 to the third is 8. This would be 3 minus 1. That's 2 factorial. That's just 2. And 8 divided by 2 is 4. See how I'm doing this kind of in my head? And some of you are going to love that. Love, hey, she's going to let us actually do mental math here. All right, so I'm lightening up a little bit. See if you can find the fourth term. Okay, you should end up with a 16 over 6 when you do that. All right, so with all these different things we've talked about, with the alternating signs, with the factorial, the perfect squares, perfect cubes, Fibonacci's, all of this is fair game. All right, so now let's see if we can write some explicit rules. Now, again, there's different terms. I like that phrase, explicit rule. They might say, find the nth term of a sequence. All right, that's just a rule where you write a sub n equals, that's the nth term. You'll even hear it called the general term. So I'm just trying to come up with the rule myself this time. So it looks like this. The nth term would be, okay, so the first thing I notice is that it's alternating signs. So I'm going to do a -1 to the n power. And that if I put in a 1, that's going to make my first term be a negative, which is what I want. So I've got that, got the alternating signs. Then I've got to figure out some way to make this go 5, 6, 7, 8. Now remember, your first term, you're going to be plugging a 1 in. So there's got to be some sort of function here where that I'm going to plug a 1 in, and it's going to get me a 5. And I'm going to plug a 2 in, and it's going to get me a 6. I'm going to plug a 3 in and get a 7, 4, 8. All right, I think I've got it. I think I'm going to do an n plus 4. That way, this is going to alternate the signs for me. When I plug in a 1, I'd have a 5. Plug in a 2, I'd have a 6, 3, 7, so forth. We've got it. Here it is. This is the explicit rule, or the nth term, or the general term. There it is. Okay, look at the next one. Looks a little fancier. Probably going to be easier, though, because it's pretty straightforward. If you look at your numerator, what do you think's going on with those? All right, that's your classic factorial. So I'm going to write n factorial, because it's going to start off, this is 1 factorial, 2 factorial, 3 factorial, 4 factorial. So that's going to work. Now let's look at your denominator. Do you recognize those numbers? Right, those are powers of 3. So it's going to be 3 to some power, 3 to some sort of a power. Well, the first term is going to be a 3 to the first. The second term is 3 squared, 3 to the third, 3 to the fourth. So it comes out just like that. And we've got our rule. All right, so that leads us to summation notation. And summation notation is used a lot in statistics and also in some probability. And as we use that summation notation, we'll need to know those general rules, explicit rules, and use that within the summation notation. All right, it looks like there's a lot going on here. This looks scary, but it's really pretty straightforward. I'm going to look at this tip right here to start with. And just how do you read this? Well, first of all, this capital S means find the sum of n terms. That's going to tell you how many terms there are. Now, since we're doing a summation, I'm going to be adding these terms together. We were putting commas between each term, but we're going to go back and now we're going to add those terms rather than just listing them. And it's read as it's the sum of, and you can see this A with that little sub I, that's your function right here. It's not going to be that basic. It's going to be more like those rules that we were working on previous slides. We're going to write that rule and put it right here. So it's going to be the sum of that with your I starting out at 1 and going until it hits N. So this is where it starts. You put 1 in, you get an answer. You put 2 in, you get an answer. You put 3 in, you get an answer. Put 4 in, and you keep going, going, going until you hit N. And that's going to be when you stop, and now you add up all those terms. Let's see, what else do you need to know? This does not have to be an I. That could be any letter. It might be a K. Just depends on what we use in this function here. Doesn't have to start at a 1. It might start at 4 and go to 7 or something like that. So let's just jump in and try one. So this first example, we're going to find, here's our function that we're going to be using. We're going to start off and let I equal 1. And then we're going to keep going, keep increasing by 1 until you get to 5. And then I'm going to list those numbers out. Now, that's what we call expanding the summation. If we expand it, we're going to list them all out. So we're going to do some mental math here. Plug 1 into that function, and you're going to get a 5. Now, don't put a comma. I actually count it wrong if you put commas, because we're doing a summation. We got to put a plus sign there. Now, put a 2 in. You're going to have a 7. Plug 3 in, and you get 9. Plug 4 in, and you'd have 8 plus 3. Plug 5 in, and you'd have 10 plus 3. And plugging 5 in is where I'm supposed to stop. So now I have these numbers that I'm supposed to add together. And I don't know, I'm just going to do some little grouping. There's a 20. Here's another 20. So that's 45. All right. So far, I haven't used a calculator for this whole lesson. And I don't think you probably should have to either, until maybe a little bit later. But a lot of this first stuff should be done without a calculator. All right, let's try again. A little fancier functions going on here. You got K going on twice, but look at this. Do you remember what this does? This is going to make us alternate the signs. Another thing, I would like you to look at this. Notice we're not starting off at 1. We're starting off at 3. How many terms do you think we're going to have if we go from 3 to 6? All right, well, it's not 6 because we didn't start off at 1. It's also not 3. A lot of people want to think 3. A lot of people count it out on their hands. I'm going to put in a 3, 4, 5, and 6. There's actually going to be 4 numbers that's going to come from this. When I decide that, and this is going to be important to recognize how many terms there are for what we're doing later, but I almost think of it like, all right, I'm going to go till I get to 6. So instead of like taking 6 minus the 3, I sit there in my mind and I think of, all right, if I'm starting at 3, what am I not including? Well, I'm not including 2 of the numbers. So I would do 6 minus 2 to say, oh, there's going to be 4 terms. That's my thinking on it. But you can count on your fingers if you got it. Okay, here we go. Let's start off. Let's put the 3 in. When I put in a 3, I know it's going to make it be negative. And then it's just going to be a 1/3. Now I'm going to put in a 4. That's going to make it go even. I'm sorry, going to be even, so make it go positive. So then I'm going to end up with a plus 1/4. Now let's plug in 5. 5 is going to make it go negative. So instead of a plus sign, I'm just going to put a minus sign, and then be a 1/5. And now I'm going to plug in 6. This is my last one. 6 is going to go positive 1/6. And then we would add these fractions up. Some are positive, some are negative. We would need a common denominator, which I think is going to be 60. They all go into 60. So this is going to be negative 20 sixtieths plus 15 sixtieths minus 12 sixtieths plus 10 sixtieths. All right, so how many sixtieths do we end up with then? Got a negative 32 and a positive 25. It's going to be a negative 7 sixtieths is what that adds up to. All right, so now let's look at trying to go the other direction. What if the summation is already expanded for you? Could you write that notation? So I'm going to give it a shot. Here we go. I'm going to put the big sigma here. And I can use an I can use an N. I guess I'm going to start with an I. And look at what the rule is. All right, so what I have here, the denominator seems pretty straightforward. I'm just going to take my I. I'm going to start it off at 1. I was kind of looking up here before I finish this, but I think I do want to start off at 1, and then 2, 3. Okay, that's going to work great. So I'm going to start off at I equals 1, and my denominator is just going to be I factorial. Now, let's see what we're doing in the numerator. It's a square root of 3, square root of 4, square root of 5. Okay, so that's just going up by ones. It's sort of like that one we did earlier. I just have to make sure that I start off in the right spot. It can't be the square root of I. That's not going to work because my first one's not square root of 1. But what if I did the square root of I plus 2? Wouldn't that get me a square root of 3 for my first term? And then when I was 2, I'd end up with a square root of 4. And I was 3, I'd get a square root of 5. I think I've got it right here. Now, I'm going to keep on going until I is equal to what? Well, this one's kind of a generic one. They didn't give me like a distinct number ending. They just said, all right, keep going to n factorial. So I'm going to keep on going until I get to n, whatever that might be. Okay, there's your summation notation for that one. All right, let's look at this next one. Looking at this, numbers are not as pretty. I don't really see like the factorial or the perfect squares or anything like that. But what I do look at here, I think the first thing I'm looking at is what am I adding to get from here to here? And this one, it looks like I'm adding 4.3. Oh, that would be another 4.3. Now that's only 2, but I'm going to say, yeah, that's probably what we're doing. If I am going to add 4.3, there's a pattern going on there that I could figure out then. So I know I'm going to have a summation. And I'm going to start, just for fun, I'm going to use an N instead of an I this time. And I've got to figure out what this function would be here to make this all happen. Now we're going to get better at this as we go through the next few days. But for this one, let's just kind of think through, see if we can figure it out. I'm adding 4.3 over and over and over. So in the first scenario, I would add it once, and then I'd add it twice, and then I'd add it 3 times. And so I think what I'm going to do is I'm going to start off at a 3.2, and then I'm going to add 4.3 over and over. So I'm going to say I'm going to add it n times. So I'm going to look at this and say, all right, once I kind of come up with a strategy that I think might work, then I'm going to test it. If I started off at 1, I'm going to put a 1 in here. I'm going to have 4.3 plus this 3.2. Ooh, that's going to get me 7.5 for my first term, and I'm going to miss out on this term. Okay, so there's different ways to handle this. There's not one right way to do summation notation. Different people write it differently, and they could all be correct, and that's fine. What I would maybe do here is, what if I didn't start off at 1? What if instead I started off at 0 and let this first term not have that? My first term would then be a 3.2. And then I'd plug in a 1, and then I'd have my 7.5, and I'd plug in a 2, and I'd have that. So that's what I'm going to do. I'm going to tweak this right here, and I'm going to start it off at 0. Now, the next part, I have to figure out, all right, so I got to keep adding it, keep doing it, but I got to know when to stop, and I have to put a number up here. What's the time that I have to stop? And that gets me to here. That's my last term. I got to figure out how to get to there. Now, some of you are already doing it in your head and you've got it figured out, or maybe in your calculator, but hang on, let me stop you for just a second. We've got to make a deal. Okay. Now, I don't want to make your life miserable, and I don't want to grade work that's going to be miserable to grade. I want to make a deal with you. If you will show me nice work using your explicit rule, typically is what that means. If you're going to show me some nice work and not just sit there and do plus 4.3, plus 4.3, plus 4.3, plus 4.3 until you get to 76.3. Don't do that to me. If you're going to do that, then I have to make these problems way trickier. And then they're a nightmare for you and they're a nightmare for me. So here's the rule, the deal. I'm not really even asking if you want to make the deal. I'm telling you, we're making a deal. You have to show me some clean, nice work using your explicit rule, not just typing stuff in your calculator. And if that's the case, I will not make problems that are nightmarish, and I will let you use your calculator on the test. If you're not showing me nice work, then I got to make these way harder, and I take away your calculator. So, do we got a deal? I thought so. Great. Okay. So here's what that means is I am trying to figure out what to put here. I need this to end up equaling 76.3. So I'm going to solve for n and see when I plug what in for n, will it get me that number there? So let's try it. I'm going to come over here to the side. This is the work that I would want to see. I want that function right there to equal 76.3. All right, so then I'm going to subtract the 3.2. So that's going to be 73.1. And then I'm going to divide by 4.3. All right, remember, if you're showing me work, I let you use your calculator. So I think, I don't have my calculator here. I think that was a 17. I hope that's right. Okay, so if n is 17, what that's telling me is that's what I'm going to put right here. I'm going to keep going through, putting in numbers in until I get to a 17, and then that's going to be the end. Now, let me ask you real quick, how many terms do you think there are if I were to expand this? All right, I hope you're saying 18. Because we started at 0, it's not 1 to 17. That would be 17 terms. But if I go 0 to 17, I'd actually have 18 terms listed out right there. Now, that wasn't the question here. Ultimately, they just wanted to know what would the summation notation be. And that's what it would be. Okay, last one. This one's for you to try on your own. Got some new things going on here. See if you can write the summation notation. So that means you have to come up with the function to put here, know where to start, know where to end. This one, I don't think there's going to be necessarily a lot of work to show. I think it's more just noticing the patterns on this one. All right, go ahead and pause the video and come up with your function. All right, here's what I came up with. First of all, the signs were alternating. And then I looked at my denominator and saw that these are all just powers of 5. Powers of 5. So I just did 5 to the n and started off with an n equals 1. Now with that, the numerator are perfect cubes. That's different than powers of a number. Powers of a number, then the exponent is up here. Perfect cubes, then this 3 would have to be here. Perfect squares, there'd be a 2 here. And this is the number that's going to change. So this is 1 cubed, 2 cubed, 3 cubed, 4 cubed. All right, that's what I've got right there. Okay, you do have a worksheet on this that is practicing this summation notation. Half of it is you doing this right here, coming up with the notation. The other half is you just evaluating the summation. It asks you to expand the summation. So I got to see the numbers with pluses and minuses, not commas, and then go ahead and tell me what the sum is. In addition to the worksheet, then you're going to finish both sides of the worksheet, and you also have a My Math Lab assignment. All right, good luck.